Here's a question that sounds like it should have an easy answer. When you're not looking at something, is it still there? You probably said yes. Of course it is. That feels so obvious it hardly sounds like a real question. Quantum mechanics never gave a single agreed answer, and the argument over that question has been going on for a century. Not on internet forums, not in pop science books, among some of the smartest physicists who ever lived. That's the story here. Because quantum mechanics does something almost no other theory does. It predicts the microscopic world with astonishing success, and at the same time, it leaves physicists arguing over what kind of reality could possibly make those predictions true. Not what the equations say. The world is. That's the problem. And if you watch the last two videos, you've already seen why it exists. Double Slit showed that particles can produce interference patterns that only make sense if something wave-like is going on. Then the pattern disappears the moment you try to pin down which path the particle took. Heisenberg showed that position and momentum can't both be made arbitrarily sharp at the same time. Those results aren't controversial. What's controversial is what they mean. Do particles have definite properties before you measure them? Is the wave function something real? It describes the world or just what we can say about the world. And when a measurement happens, what actually changes? That's the fight quantum mechanics never settled, because the math gives you probabilities for outcomes, very good ones. What it doesn't automatically give you is a single agreed picture of what's happening in between, or what kind of reality gives rise to those outcomes at all. That's why this argument exists. Not because quantum mechanics failed, it worked too well while leaving the picture underneath unresolved. So what are the actual options? The first is the one that shaped the early history of the theory, what we now loosely call Copenhagen. That label is messier than people think. It was never one perfectly clean doctrine that every founder stated the same way, but the broad instinct is familiar. Quantum mechanics is a tool for predicting what measurements will show. Use it, trust the formalism, and be careful about demanding a classical story of what the particle is really doing when no measurement is being made. That demand may be exactly what quantum mechanics is telling you to give up. You can see why this became so influential. It's disciplined, it's pragmatic. It says stop trying to force the microscopic world into the categories that were built for baseballs and planets. But you can also see why so many people hated it, because it can sound like the theory works brilliantly while the question of what's really there gets pushed off the table. Einstein hated that, and he wasn't alone. If a theory is supposed to describe the world, a lot of physicists wanted more than a rule book for what instruments will say. They wanted a picture. That brings us to Hugh Everett. In 1957, Everett proposed a very different answer. Don't add collapse, don't carve reality in two, just take the wave function seriously all the way down. In Everett's view, the wave function never suddenly stops obeying the normal quantum rules when a measurement happens. It keeps evolving, always. What we call a measurement outcome is then part of a larger quantum state in which different outcomes are represented in different relative states, what later became famous as many worlds. That idea has a very obvious appeal. No special moment where physics breaks its own rules, no magical collapse, no divide between normal quantum evolution and measurement. The theory just keeps going. The price is obvious too. You now have to accept a reality far stranger than ordinary common sense wants. Because if the wave function never collapses, then what looks like one outcome from your point of view is part of a much larger branching structure. That's a huge conceptual cost. But it buys Everett something important. The laws stay uniform, no exception right at the moment of observation. Then there's a third answer, pilot wave. More precisely, de Broglie-Bohm mechanics, or Bohmian mechanics. This one says the particle really is somewhere. It has a definite position at all times, and its motion is guided by the wave function, which still evolves by Schrödinger's equation. In that picture, double slit becomes very concrete. The wave passes through both slits, the particle goes through one, but the guiding wave still shapes the particle's trajectory so that, across many runs, the interference pattern appears. So you get real particles and a real guiding structure without giving up the quantum predictions. That's why Bohmian mechanics has such pull. It gives you back something Copenhagen seemed to take away. A world where there's something there, somewhere, doing something, even when nobody's looking. But it doesn't give you classical comfort for free. The price is non-locality. The overall quantum state links distant parts of the system in a way classical physics never would. So Bohm gives you a more concrete ontology, but only by accepting a world stranger than classical mechanics in a different way. And that's why nobody can agree on what quantum mechanics means. Not because physicists don't know the equations, not because the experiments failed, because the same successful formalism supports radically different pictures of reality. One says, stop demanding a classical story underneath. One says, keep the wave function and accept branching reality. One says, keep real particles and accept non-local guidance. Three very different worlds, one mathematical framework. That should bother you, because it means the theory tells us how to calculate with extraordinary power while leaving the nature of reality itself underdetermined. That's not normal, and it's why this argument never stayed in the past. Quantum computing, quantum cryptography, and quantum sensing all use quantum mechanics every day without resolving it. The technology works, the meaning doesn't. And the experiment that forced that instability into the open, the one that ruled out local hidden variable explanations under specific assumptions, is the subject of the next video. If you found this useful, a like and subscribe helps us keep making more of these videos. Thanks for watching.